Right. So vertical circular motion. So again, discussing the specific case of the vertical circular motion of a particle attached by a massless thread to a point such that it can rotate about that point P. Let's say, let's take that point as O. So it can rotate about that point O freely, but in a vertical plane. This is the particle P, mass M, is a thread of length L. So what we had understood last time, that if we give it a horizontal impulse so that it develops a velocity, let's say V naught at the bottom, in the moment we give it that velocity V naught, it sets off into a vertical circular path such that by the time it has made an angular displacement theta, we can find out by application of conservation of mechanical energy, and find out that its speed becomes square root of V naught square minus 2gh, where h in this case will become L into 1 minus cos theta. This is a sort of standard expression, so you should just remember this. Okay. Then the other thing is that the tension in the thread at this point of time will therefore become mg cos theta minus mv square by L. So this second expression is telling you that even in case V becomes 0, that is, a particle stops at a certain height before it reaches theta equal to 90 degrees, the tension in the thread will not become 0. The thread will remain taut, or the thread will remain tight, and therefore the system will behave basically like a pendulum in oscillation. So from these two expressions, you can see that. Okay, so from this, you can understand that for V naught less than equal to root 2gl, V becomes 0 at some theta less than equal to pi by 2. Okay. And at the position at which V becomes 0, tension becomes mg cos theta, and tangential acceleration is g sin theta. Okay. So the particle momentarily stops at that position and comes back. So the condition for that to happen is that V naught should be less than equal to root 2gl. So this. Now we'll move ahead. So this we've seen in the last lecture. Okay, now we'll
Sir?
move on. Yeah.
So root 2gl or root 2gh?
Root 2gl
Or root 2gh, sir.
h2 is the height from this point. No? But we are finding the condition. See, h in this diagram is this one. But we are finding the condition for it to at least reach 9. I mean, the condition that it should not go beyond 90 degrees. Okay. Understanding the point? So if I take V naught equal to root 2gl, this h is actually becoming equal to L. So it's reaching the 90-degree position.
Yeah, okay, okay.
Right? So it's like the boundary condition. When it's root 2gl, it's that situation where it reaches 90 degrees. If it's less than root 2gl, then this h will be less than L. Na? So it will stop somewhere before 90 degrees.
Okay, sir.
Right, okay. So basically that's the point, that less than equal to pi by 2 for V naught less than equal to root 2gl. Okay, so that equality. So the other thing you'll also see is that if it reaches the 90-degree position and stops at that point, that is V naught is equal to root 2gl, momentarily at that position even the tension becomes 0. So just for an instant the particle has stopped and it's in free fall. But the moment it comes back from 90 to 89 point something, again the tension becomes non-zero and it gets back into circular motion. Okay, so this point is also clear, I hope.
Yes, sir.
Okay, So now let's see what happens if we make the velocity more than root 2 GL. So it crosses the 90-degree position. Okay, so for V naught greater than root 2 GL, the particle crosses or goes beyond. Now, for some theta greater than pi by 2, if you look at the free body diagram, you'll notice one difference now. The way tension acts is different. So if we look at the particle at a position beyond the 90-degree position, so it had started from here with a V naught greater than root 2 GL. It crossed the 90 degrees and at some theta greater than pi by 2, the particle now has tangential velocity V. So the difference now is that mg and tension, mg cos theta, or mg is vertical component, you can say, that has a centripetal component, whereas earlier that had a component which was away from the center, that was centrifugal, but now it is centripetal in nature, it's pointing towards the center. So this is our mg and this is our tension. So in fact, what we can do is, just to make things convenient, since theta is an obtuse angle, we can express this angle as something, let's say beta. Okay. So at theta greater than 90, this angle becomes beta. So if you look at the free body diagram equations, we have mg cos beta plus tension is equal to mv square by L. So you can see that tension is mv square by L minus mg cos beta. You can see how this equation is different from the equation when theta is less than 90. Here tension was mg cos theta minus mv square by L. So even if v became 0, there was no problem. There was some tension. But here it is mv square by L minus some component of mg. So even before v becomes 0, at some non-zero value of v, there is a probability that the tension can become 0 because it's mv square by L minus mg cos beta. So if the tension becomes 0, the thread will slacken. So it will be that situation that you push it with some velocity here. It goes in circular motion up to this point, but then the thread loses tension. So the particle basically falls in a projectile motion. It does not continue in vertical circular motion. Okay, so that's how this situation becomes different. Okay.
But sir, why will that thread lose tension?
See the equation, it's mv square by L minus mg cos beta. Na? So if
That
v,
I understood. But while moving, so the object will always have inertia, right? Outwards direction.
so the inertia of the object wants to make it continue with v in the tangential direction, na, beta? But the inertia cannot make it move in circular motion, and the inertia cannot be responsible for tension in the thread. You're understanding my point?
So then what is contributing the centrifugal force?
No, centrifugal force is a pseudo force, beta. That is if you get into the particles frame. So if you get into the particles frame, centrifugal force is pushing it radially outwards. Okay, and that is what is creating tension in the thread. But there's mg cos beta also pushing it radially inwards, no? So if
Yes,
your
sir.
centrifugal force becomes equal to your mg cos beta, there is no tension in the thread. There isn't enough centrifugal force to pull it outwards.
Okay, sir. Okay.
Understood the point, no? So
Yes, sir. I
if
got it.
you compare this situation when it's at an obtuse theta with respect to this position, when it was at an acute theta, we'll understand the difference. Here, what is happening now? mg's outward component or mg's cos component, or you can say mg's radial component, was contributing to keeping the thread tight. But here, mg's radial component is actually contributing to loosening the thread.
Yes,
Understood?
sir.
So that's why there's a danger of the thread becoming loose. If it does not have enough speed, there won't be enough centrifugal force. Or when we look in the ground frame, the centripetal acceleration will not be large enough to make the tension in the thread necessary. Okay. So we have this equation, okay, from FBD, that is, okay, and also from work by energy and from conservation of mechanical energy. Okay. So now we have to take this total height to compare it with the initial speed below. We have to consider this height. So half mv square, the kinetic energy at this point, is the initial kinetic energy minus the gain in gravitational potential energy. So V is equal to square root of V naught square minus 2gh, but here h will become L plus L cos beta. Okay, because this much part is L cos beta. This much part below is L. So this is our second equation. So again, if you observe what is happening to tension in the first equation, you can see that as the particle is going up beyond 90 degrees, from 90 towards 180 degrees, from this 90-degree position to the topmost point or the zenith point of the vertical circular motion, you can see that your mg cos beta term is increasing more and more because beta is reducing from 90 towards 0. And your V continues to decrease because you're gaining height. So obviously your kinetic energy is decreasing. So V is decreasing. So tension is becoming lesser and lesser. Okay, so from equation 1 and 2, you can see that the speed also continuously decreases. Okay. So this is already there. Now also the thing is that equation 1 is also showing you that there is a possibility that if your V is not sufficiently high at some point, mg cos beta and mv square by L cancel each other and the tension becomes 0. So the string slackens. Now once the string will slacken at a certain point, the particle's next part of the motion will not be circular anymore because this, if the string is slackened, that constraint is gone. You know, that it has to have a fixed distance from the point O where the thread is attached over here. It does not have that constraint anymore. So if it does not have that constraint anymore, that the distance OP is fixed because the string is not taut or tight anymore, then it's not a circular motion from that point onwards. In fact, if you think about the free body diagram, if the tension becomes 0, then there's only gravity acting on it. So it's motion under gravity. So it's basically a projectile motion from that point. Okay, so first just understand these two equations and this point I've written below. Okay, this point here. Then we'll also understand the condition for the thread to slacken. Okay, so next let's look at that point. So also from equation 1, if mv square by L becomes equal to mg cos beta at some theta, then tension will be zero at such a position. So tension becoming zero means that the string becomes slack. So if this happens, then the particle will not continue circular motion. Instead, it will be in a projectile free fall. It will not be in a vertical free fall because it has some velocity, but it will just be like a projectile motion from there onwards. It will progress into a projectile path. So basically, if the tension becomes zero at such a position, but it's having some velocity, okay, it's just that the velocity is not large enough to maintain the tension in the thread because of that mg cos theta's cos beta's component coming in. So from this point onwards, the path of the particle will be a projectile. So it had come up to this point in a circular path, but from this point onwards, it does not continue in circular path. Instead, it falls in a projectile path. So next we will look at the condition for this not to happen. Okay, condition for completion of vertical circular motion. So we want this thing that it should complete the circular motion in that vertical plane. Tension should be non-zero at all points. It is from theta equal to 0 to pi. Because thereafter the motion will be like a mirror image of this side. So we have ensured, okay, so since tension continuously decreases from theta equal to 0 to pi, if tension is greater than or even equal to 0 at the highest point, theta equal to pi, then tension will be greater than 0 at all points. 4 theta equal to pi. So the critical point for us becomes the highest point. And critical condition is that tension should be greater than or just about even equal to 0 is okay at theta equal to pi. So now what I will set you to do is that, which we'll derive ourselves also, but find the condition on V0, that is the speed at the lowest position, so that tension should be greater than equal to 0 at theta equal to pi. Okay. Try this yourself.
So,
Yes.
so if tension is equal to 0 at theta equals pi, then the thread will become slack, right?
Momentarily the thread will become slack, but remember it will have a horizontal velocity at that point. No? So just for a moment it goes into a projectile path with a horizontal projection velocity, but next moment that string again becomes tight. You understood? No?
Okay, sir. Okay, sir. Yes, sir.
Because it's like, at theta equal to pi minus some delta theta, where delta theta is a very small angle, the tension is greater than 0, no? Because it's 0 only at the highest point. So when it crosses that pi and goes to pi plus delta theta also, again the tension becomes non-zero. So it's just like as it's passing through theta equal to pi, momentarily the tension is 0 for an instant, but it still will continue in vertical circular path. Or it's reached theta equal to pi, so it's in a vertical circular path, right?
Okay, sir. Yes.
Yeah, Janvi, that is a condition for V at the highest point. Okay, that's correct. So now you back calculate what is the condition on V0 at the lowest point, so that happens. Okay.
Okay, sir.
Yeah, what you calculated is correct. So V at the highest point should be at least that much. Greater than equal to 0 tension के लिए V at the highest point should be greater than equal to the value. So from that you can back calculate that what is the minimum velocity required at the lowest point V0. Okay.
Yes, sir, I am.
So once you got that, that's a like standard value that we'll have to keep in mind. Okay. Right, very good. So getting the correct answers, you will see that the condition is root 5 GL, okay, at the lowest point, V naught. So first of all, you check out the condition for V at the highest point. Okay. So if the particle has, we assume that it's reached this, okay, theta equal to pi position. So that means the string has not slackened anywhere before that. Had some V naught here, but now by the time it's reached here, it needs to have some speed, okay, because without that, there's no way there'll be tension in the thread. So the condition is not about reaching that point actually. The condition is about reaching that point with the string being tight. So we want the tension in the thread to be a non-zero quantity, or just about zero at the highest point is also okay. So T plus mg at theta equal to pi, T plus mg is equal to centripetal force. Okay, so therefore, for T to be greater than zero, greater than equal to zero, mv square by L should be greater than equal to mg. So the velocity at such a point should have a magnitude of greater than equal to root GL. Now compare that with the lowest point. Therefore, this is the condition on V. Okay, right. Now from conservation of energy, we have now comparatively H here is 2L going from here to here. Okay, so something like this. When you substitute H as 2L, therefore substituting in equation 1, this should be greater than equal to GL for, or we can also write it like this, that V which equals to square root of V naught square minus 4 GL should be greater than equal to root GL. For the thread to be taut all the way. The critical condition we get for velocity at the lowest point is root 5 GL. So this is the critical condition for completion of the vertical circular motion. Okay, so this is an extremely important derivation for you to understand conceptually and also to remember this value for this case from now on, that root 5 GL, so that you can do the analysis of this in a given numerical question directly without having to do this derivation on the spot. Okay. You should remember this value.
Sir, how did you get that 4 GL?
Okay, so now based on this, we can list a set of different conditions, okay, of how the circular motion will progress. Yeah, I mean centrifugal force, it's one and the same thing. No? Like if we are in the particles frame, then centrifugal force is acting outwards. So for example, Bhavika, at a point like this, if the particle has a velocity v, so in the frame of the particle, if we are looking at it in the rotating frame of the particle, we will see centrifugal force acts like this, mv square by L, and mg acts like this, and tension acts like this. So if mv square by L becomes less than mg cos beta, less than equal to, then the thread slacks. Tension has become zero.
So beta should be on the left side.
Yeah. Sorry, come again.
So beta should be on the left side of mg, like in the diagram.
So yeah, beta should be the angle that the thread makes with the vertical. Yeah. Okay, so yeah, I'll scroll back, but Bhavika, this is clear now. If we are using the rotating frame for an analysis. Okay. Okay, so people are writing this down, so I'll just let you complete this first. Okay, let's come to this now. So the different conditions, okay, or you can say the different cases of the phenomena that can occur here based on the value of V naught. So in the first case, if we take a situation where the speed at the lowest point, if V naught is less than root 2 GL, we give it an initial speed which is less than root 2 GL, then what will happen is that it will come to some theta before it reaches 90 degrees. It will come to some theta where it stops. Then at some theta less than 90 degrees, V is equal to 0 momentarily. And tension at that point will become mg cos theta. So it will have V equal to 0 at this point, but tangential acceleration in this direction of g cos theta, and then it will go back here. So it would have come like this, and then it will return back like this. On the return journey, it will again have the speed V naught, go to this position, symmetrical theta on the other side, and then return back. And I mean, assuming if there's no air resistance and no friction at the hinge point O, this motion will continue forever. So it will be like a perpetual pendulum. But that is if V naught is less than. Okay. Now, second, we'll take like an in-between case where if V naught is exactly equal to root 2 GA, then the maximum theta is equal to pi by 2, and at theta equal to pi by 2, V is equal to 0 and tension also is equal to 0, and tangential acceleration is g downwards momentarily. So there also it is going to go back and forth. This kind of a motion.
So,
Yes,
so in the first case, tangential acceleration should be g sine theta or g cos theta.
G sine theta. Sorry, my mistake. Tension is mg cos theta, right? And the tangential acceleration will become g sine theta momentarily. Okay. So this case also it will behave like a pendulum, but with what we call an angular amplitude of 90 degrees on either side. So the only difference between the first and second case is that in the second case, momentarily tension is 0, okay, at the maximum displacement from mean position, but here tension is non-zero, but the minimum value. Anywhere else in the motion, the tension is greater than this mg cos theta. Okay, now let's come to the third case, where if the speed we give is greater than root 2 GL, so it's going past the 90-degree position, but it's less than root 5 GL. So if it is less than root 5 GL, it will not reach theta equal to pi. The string will slacken at some point before that. So if we give such a V naught at the lowest position, then it crosses the 90-degree position, but never makes it in circular motion to the 180-degree position. Instead, at some theta, before it reaches this point, it has a speed, but the tension becomes zero. From there onwards, it falls in a projectile path. So at some theta, between pi by 2 and pi, the thread will slacken and the particle falls into a projectile instead of continuing in circular motion. So the condition for this to happen is that mg cos beta should be equal to mv square by L at some theta equal to pi minus beta. And of course, you have so when we work out numerical problems, we'll be using these equations to understand at which particular value of theta the string is slackening if this condition is satisfied. We can calculate that by using these two equations I've tick marked below. Okay, so it's very imperative that you remember these cases numerically, the conditions on the cases, root 5 GL and root 2 GL, these two values, so that you know that comparing with these two values for a given value of V naught at the lowest point, which category the actual path or the motion is falling into, whether it's a completion of vertical circular motion or it's a pendulum type motion, or is this in between case where it goes beyond 90 but at some stage it goes out of of circular motion and falls into a projectile path. So the fourth and final condition is that if V naught is greater than equal to root 5 GL, this is the condition for it to complete circular motion. Okay. And tension is greater than equal to 0 for all points. So for V naught equal to root 5 GL, tension is 0 momentarily at theta equal to pi. But that doesn't mean it goes out of projectile motion, because again it picks up tension the moment it crosses the 180-degree position. Okay, so let's look at this with a numerical example. So we have the standard situation now given that the length of the thread is 10 meters. The acceleration due to gravity is 10 meters per second square. Find the path of the particle and the maximum height in meters from the given position. And also the maximum and minimum tension in the thread. If V naught is 10 meters per second, and if V naught is 20 meters per second, and if V naught is 30 meters per second. So three different cases. Okay, you will see that these values are given such that they correspond to different cases in terms of how the circular motion progresses and up to what point it's a circular motion. So what we have to do is you have to understand how these numerical values of V naught correspond to the above theoretical cases that we've developed, that root 2 GL condition, that root 5 GL condition, and from that you'll understand that at which of the points what is happening exactly. So just try out this question, people. So you can just start by figuring out the theta max for each of the cases ABC. You can just send me that in the text message. I'll verify for you if that's correct.
So done.
So
Yes.
so
What is happening in the part A? Like, is it behaving like a pendulum or it's crossing 90
so
degrees?
V naught is less than root 2GL, so it behaves like a
Yes.
pendulum.
So it's behaving like a pendulum. So now how will you calculate the maximum theta it goes to?
Sir, height, no?
Yeah, it is a point where V becomes 0. Because
Yes.
the pendulum's extreme position is where the particle momentarily stops. It's not where tension becomes 0, because tension does not become 0.
L minus L cos theta.
Yes, L into 1 minus cos theta, that should become equal to, 2GL into 1 minus cos theta should
Yes,
become
sir.
equal to V naught square. From that you'll see, you'll get the theta max. Okay. Whereas B case, what is happening? Your V naught is greater than root 2GL, but less than root 5. You're getting that?
Yes, sir.
Yes, sir.
20 is less than root 500, no?
Yes, sir.
Or 10 root 5, but greater than 10 root 2. So it's going to cross the 90-degree position, but it will somewhere the string will slacken. So the whole thing will come apart in that sense. Okay. So how will you find the position where that happens next, the theta max? You have to find the condition for tension to become 0, not V0, but for the tension to become 0. So just refer to this condition that I've written above, that the two tick marks. At the position where tension becomes 0, mg cos beta, where beta is pi minus theta, that one should become equal to mv square by L, and V will come from work energy. Okay. Whereas the 30 case you will see is greater than root 5 GA. So it's going to complete vertical circular motion.
So
So
can we say that no matter what type of path, the tension will always be the least at the highest point of the motion?
Yes, tension will always be least at the highest point. In the case of pendulum, it will be least but not 0. Okay. In the case between root 2 GL and root 5 GL, it will actually become 0. But technically, that will not be the highest point. It will be the highest point of circular motion, but the particle will continue going up for a little bit of time in the projectile motion. But yes, the last point of circular path, in that the tension will become 0, which is the lowest value. Yes, Ibrahim, you had some question?
so like you've told us to find the maximum tension in the thread. So that will always be at the starting point, right?
Yes, maximum tension you will always see is at the position at which mg and tension are opposite to each other and speed is maximum. So that is the lowest position. So
Yes, sir.
maximum tension always in all the above situations will be equal to mv naught square by L plus mg at the lowest point.
Yes, sir.
Or if you're in the frame of the moving particle, you can see centrifugal force and mg are both acting outwards at the lowest point. And plus centrifugal force is maximum because V is maximum at the lowest point, work energy wise. For that, you need the mass of the particle. So just write the tensions in terms of m, or we can assume some value of mass. Take the particle's mass to be, let's say, 1 kg or something. So you can then get the numerical value in newtons for the tensions. So see, for some like this, the strategy that we can develop is like this, that we first see the critical values. What are the critical values? Root 2 GL, which in this case is 10 root 2 or approximately 14.1 meters per second. Okay. And root 5 GL, which is 10 root 5, which will become approximately 23 point something, right? So you can now compare all of these and see which falls in which category. Third case, V naught is greater than root 5 GL. So it completes vertical circular motion. And in fact, tension will be greater than 0 at the highest point. So now that we are through with that, now let's find this theta max for each of these. This is when the tension will be maximum. So at the lowest point, the tension will be maximum. Yeah, mass 1 kg. Now we come to this. So here V is becoming 0. So V is becoming 0 means so this is the maximum angular displacement. and tension is equal to mg cos theta is equal to mg by 2, which will be 5 newtons. So this will be the maximum tension and this will be the minimum tension in this particular case. And this is the maximum angular displacement. Okay, so hope this case is clear. Okay, so this is done. Now let's come to the second case. The second case is the trickiest one of all to solve. Okay, so when we are taking V naught as, what was it, 20 meters per second. So we can see that V naught is greater than root 2 GL, but less than root 5 GL. So we'll have to assume that what happens here is something like this. that at some theta in between the 90 and the 180-degree position, the string will suddenly slacken. So as usual, it's more convenient to take this angle beta and work beta out, and then okay, so at the lowest position, the tension is again the maximum. So be the maximum tension, and that will be equal to here 10 plus so 20 square by 10, so 40. So 50 newtons will be the maximum tension at which will be at the lowest position. Okay. Now at this position here, we are assuming tension is becoming zero. So the particle still has a momentum, but it loses the circular path, and from there onwards it goes into a projectile path. So the condition for tension to become zero is that mg's centripetal component, mg cos beta, should be equal to mv square by n. Equation 1. Okay, so from this we get that v square is equal to gl cos beta, and half mv square is equal to half mv naught square minus mgh, where h is equal to L1 plus cos beta. So from this we get that v square is equal to v naught square minus 2gl into 1 plus cos beta. So now solve these together. Now put the values in and you'll get the numerical value of cos beta. See, GL is 100, cos beta is equal to V naught square. So that's 20 square minus, so we get cos beta is equal to 4 minus 2 into 1 plus cos beta. So 3 cos beta is equal to 2. Right? So beta is cos inverse 2 by 3. So we can leave the answer this way. That's cos inverse 0.67. If you want the numerical value, then we can just use a table or a scientific calculator. So I'm doing that. For accuracy, I'll take it 0.667 cos inverse. Should be about 48 degrees. So now you can see that the maximum theta it's about 132 degrees. Okay. So I think we got more or less everything we are looking for. Maximum tension, minimum tension, and maximum angular displacement We have to also find the maximum height. Okay. So I'll come to that. The maximum height will not be L1 plus cos theta, because beyond that also it goes into a projectile motion. So that's also an interesting question. Maximum height from the initial position. So for that we have to consider the part of the motion after the spring slackens also, because for a very short duration of time, it continues gaining height before it finally starts descending, even after the string is slackened. But hope this calculation is clear first of all to all of you. Okay.
Yes, sir.
Yeah. Now also try to see how you will calculate the maximum height. What would be the easiest way? Okay, the hint to you is that at the time when the thread slackens, the velocity is tangential to the thread. So you know the value of velocity because you have calculated cos beta's value at that point. So you know v square is gl cos beta from equation 1. So you know v and you know the direction of v. So it's easy to work out that from there in the projectile path, how much further up it's going.
Sir, is it 50/9?
ये ले इसमें बैठ के सुन सब तो है तू ही निकल गया आदि व्हाट इज रॉन्ग विथ यू आदित्य
Okay, so let's anybody got this maximum height?
So 50 by 9.
Sorry, come again, beta.
50 by 9.
51?
50 by 9.
50 by 9. So that is almost how much? 5 point.
Oh, sorry, sir. 50 by 27.
Okay. Meaning, but from the lowest point, no? You are calculating of the projectile motion.
Yes,
Yeah,
sir.
yeah. Okay, so just add that L1 plus cos beta to that.
We
Yeah.
have to add 20.
So basically now I've got this position. How much was this? Is about 48 degrees now. So that will look something like this. Just about more than 45. So this is where the string is slackening. Okay. This V0 was 20 meters per second. And at this maximum theta, which was about 132 degrees. So at this point of time, what was the speed? The V was, you can see in the above equation, it was root GL cos beta. And beta was cos inverse 2 by 3. So V was 10 root 2 by 3. Now you'll also understand that at this position, because this angle, pi minus theta was beta. Therefore, now this angle will be beta. So from this point onwards, when it goes into a projectile motion, whenever it reaches the highest point of that projectile path, its velocity will be what? The horizontal component of this V. So we can make use of that also. Okay. So this is our critical highest point. At this point, the velocity will be a purely horizontal velocity.
Sir, I can't see the screen anymore.
Just,
Yes.
yeah, it's visible now. No?
Yes.
Yes,
Sir.
sir.
Okay. So when it reaches this critical highest point, what will be the velocity? It will be the horizontal component of this V. So it will be this Vx, which is V cos beta. So now we can do something interesting to get a direct answer. What I'm looking for is this maximum height only, no? From where it started. So I'll call this as capital H. There are many different ways in which we can calculate this capital H. For example, you can also calculate it in terms of this. Okay. So we can write H as L1 plus cos beta. Just a moment, people. I'll reshare the file. Okay, so the V at this point was root GL cos beta. So that was this. Okay. Yes, okay. So one way we can calculate this as this plus small h for the projectile motion. So small h is v square sine square beta by 2g. Or another way to calculate this is apply conservation of mechanical energy from start to the highest point. So we will have that half m vx square at that highest point should be equal to half m v naught square at the lowest starting point minus mg capital H. Will give us the formula for capital H directly. So we'll see that H will become v naught square minus vx square at that highest point divided by 2g. Okay. And vx at that highest point, remember, is v cos beta. And v itself was how much? V was 10 root 20 square minus 4 by 9 into v square, which is 100 into 2 by 3. So this is a calculation that I'm getting. Just verify it once, and if you separately calculated the projectile's highest point and L1 plus cos beta, you can try it this way also. So you can see that H falls short of 2L because it's not completing the vertical circular motion. But at the same time, it does go a certain distance, almost 2 meters further up, even after the string slackens. So this is a point where a lot of people make the mistake of calculating the maximum height as L into 1 plus cos beta, forgetting the fact that there is a projectile component of motion after the string slackens also. There's a continued rise in height for a bit of time. Okay, so this one is clear, I hope, and let's move on to the last part. Last part is again easy because you know it will complete vertical circular motion, and since B is greater than V naught rather is greater than root 5 GL, so it not only completes vertical circular motion but also, and at the highest point, tension will be greater than 0, but that will be the minimum tension. So just need to quickly numerically apply the work energy concept. So this is where it started its circular motion from. The maximum tension was at the lowest point. This time you'll see it's quite a large amount of tension. You compare it with the weight, it will be a large multiple of the weight. This T naught. So you can see it's 10 times the weight because it will become 90 plus 10, 100 newtons. This is the maximum tension. Remember, mg is just 10 newtons, so it's 10 times the weight at the lowest point. Now, when it reaches the highest point, it has the minimum speed. Yeah. This vertical height it has climbed is 2a. So we have this is the speed at the highest point. And this tension that it will have here, this will be the minimum tension. You can see it has quite a large amount of tension even at the highest point because it has quite a large speed. So the tension ranges between 40 newtons every time it's at the highest point and 100 newtons every time it's at the lowest point. And the speed ranges between this 22 meters per second at the highest point and 30 meters per second at the lowest point. Okay, so people, with that, we conclude this question. Hope this is clear to all of you.
Yes, sir.
Yes, sir.
Okay, so now go ahead and complete circular motion this week, especially vertical circular motion questions from H.C. Verma also, but it's in the work energy chapter towards the end. And also there are some quite typical type of questions in the last part of the circular motions chapter of H.C. Verma that has to do with dynamics of circular motion, and we have those kind of situations where in a rotating frame you have to consider an Atwood machine and all that. So centrifugal force applications. So try to work out all those things, and I think most of you are having physical doubt sessions in your respective centers. So also try to clear questions, doubts and all that in the physical doubt sessions. If anything is required, we'll discuss in the next lecture. But we will also look to progress with the next chapter after circular motion for us, which will be center of mass. Okay, so next lecture onwards, we'll be starting center of mass.
So we're done with this?
Yeah, we are done with circular motion. Congratulations, one more chapter done.
Okay, sir.
So now from the next topic, only offline lectures, right?
Yes, from the next topic onwards, we will be looking at doing offline lectures also, right?
Let's just see. Okay. I got it. Thank you, sir.
Okay. So that's it for today, people. Wish you all the best.
Thank you, sir. Bye, sir.
Thank you, sir. Bye, sir.
Thank you, sir. Bye, sir.